Welcome back to the blackboard. We are going to do a couple examples on subspaces. As I mentioned before, we're only going to focus on subspaces since vector space, you just have to check the 10 axiom, which are pretty straightforward, but with subspaces, it gets a little trickier. So we're going to go ahead and do this first example. And in this example, it tells us if the set of vectors in R3 such that x1 squared plus x2 squared plus x3 squared is equal to 1, a subspace of R to the n. So, as I mentioned in the lecture, for subspaces, all we really have to do is check three conditions. So the first one is if the two vectors in the space, when added together, is also in the set. And then the other one is if you multiply that vector by some constant, the new vector will also be in the set. And then the third one is if 0 is in it. 0 in set. So these are like the three conditions we have to check in order to know if a particular set is a subspace. And we don't have to check if the vector is a vector space, because if we're looking for a subset, that means the set that we're looking at is part of a bigger set in which that set is a vector space. So to put it in visual terms, you'll have your vector space, this part here, and then this would be your subspace. So the subspace is in a vector space, so that's why you don't really have to check any conditions of a vector space. You just have to check these three conditions. So I'm going to get into the example, and for this example, what we can do is pretty much do it by an actual example. So we're gonna let v1 is going to be equal to a vector. It's going to be in the set. We're just going to call this set S, and it's going to be 1 0 and 0, and then v2 is going to be 0 1 0. And we know this is in the set of vectors in R3 because when you check this condition, you'll have 1 squared plus 0 plus 0, which is 1, and then 0 plus 1 squared plus 0, which is also 1. So now we want to check if you add them together, if it equals to a vector that's also in the set. So we're going to have tv1 plus tv2, and so that's going to be 1 0 0 plus 0 not 0 0 1 0. And so this is the same as 1 plus 0, 0 plus 1, and then 0 plus 0, and that will give us 1 1 0. And so now we have to check if is it in set or in the set S that we defined here. And so to check if it's in set S, again, we have to check if this condition is satisfied. And so what you're going to see now, that it doesn't satisfy the condition because you have 1 squared plus 1 squared plus 0. So that'll be 1 plus 1, which is 2. And it wanted to or the condition for this vector is that it has to equal to 1, but it's not, since 2 is not equal to 1. So what this means is that this set is not a subset of R to the n. And so this is another way you can answer these type of questions, since you don't necessarily have to check the general conditions. If you can do it by through an example, so like how I did here, have a little example with having two arbitrary vectors that satisfy the condition, and then show that when added together it is not equal to another vector in that set, then it just proves that the entire set is not a subspace. And the same thing applies if you were to multiply it by a constant. So we would did multiplication by a constant. We're just going to use v1. We're going to have some constant k multiplied by 1, 0, 0. And that is going to be equal to k 0, 0. And so now when you check the condition, you'll have k squared plus 0 plus 0. And that's going to equal k squared, but this will only be true if k is equal to 1. If it's equal to anything else, then it doesn't satisfy the condition of that equaling to 1. So if k was 2, you'll have 2 squared plus 0 plus 0, and that'll just be 4, and 4 is definitely not equal to 1. And so yeah, that's one way you can answer these type of questions with subspaces. And so now we're gonna move on to the next example. So in our next example, we have to find which of these sets are a subspace of the vector space of differential functions. So this is a little bit of, or you need to have a little bit of calculus background to know what a differential function is. But I'm gonna make the assumption that you do know what they are, and we're just gonna go ahead and do the example. So the first one is a set of functions that satisfy f prime of x is equal to x squared. So one way to, or an easy way to show this, if this set is a subspace, is to just let f of x equal to 0 for every x. So that means f prime of x, because f of x is just equal to a constant, and we know that the derivative of a constant is just 0, well, and then derivative of 0 is also 0, f prime of x is equal to 0, which is not a function of x squared. So that means this set is not a subspace. So that was pretty easy. So now the last part of this example is a set of functions y of t that satisfies y double prime plus 2y prime plus y is equal to 0. So what this basically is saying is that given this differential function, the solution of this differential equation is y of t. So now we have to show that it's closed under addition, subtraction, addition, scalar multiplication, and then it has 0. So the 0 one, it's really easy to check. So if we let y of t is equal to 0, then the differential function, we know that y prime and y double prime is equal to 0 because they're all constants. When you plug it in the differential equation, you get 0 plus 2 times 0, which is 0, plus 0, which is equal to 0, and we have 0 is equal to 0. So the 0 vector is in this set. So now we're gonna do the, I guess, longer part. So it's gonna be closed under addition and then scalar multiplication. So for addition, closed under addition, we're gonna have two differential equations, and we're just gonna have it y double prime plus 2y prime plus y is equal to 0, and then x double prime plus 2x prime plus x is equal to 0. And so now we're gonna add these two up, and so we're gonna get y double prime plus 2y prime plus y plus x double prime plus 2x prime plus x is equal to 0 plus, well, I guess plus 0. So this is going to be 0. And so now what we can do is we can group the like terms together, or not like terms, kind of group certain derivatives together. So we'll have y double prime plus x double prime plus 2y prime plus 2x prime, then plus x plus y is equal to 0. And so if you remember when it comes with derivatives, that the derivative of f plus the derivative of g is the same as the derivative of f plus g. This can be used, or this concept can be used here. And so that means we can have a function y double prime plus x double prime plus 2y prime plus 2x prime plus x plus y equal to 0, such that the solution will equal to h of x, where h of x is going to be equal to, oh, it's not x, my bad, h of t, because it's a function of time, h of t equal to y of t plus x of t. And so what we did here is we should show that this is closed under addition, because from the beginning part we had our t of y and then our t of x. We put them together, create a new function, and that new function will have a solution, h of t, where h of t is y of t plus x of t, which is also the same as ty plus x. So it is closed under addition. And so now for the multiplication, closed under. So we're going to let k equal to, or not, we're going to let k be any real number. And so we're going to use the function y. So we're given a differential equation y double prime plus 2y prime plus y, and we're just multiplying it by k. and then this is also equal to k times 0. So this is automatically going to go to 0. And then here we'll have k y double prime plus 2y, not 2y, 2k y prime plus ky is equal to 0. So with differential equations, when you find a solution, if we have any solution, so we know the solution of the original, or just without the k. So without k, the solution is just y of t. And then the unique thing about differential equations is, given any differential equation with some known solution, in this case it would be y, if you multiply the differential equation by any constant, then that solution will also be the same as the original solution, just multiplied with that same constant. So that means without the solution we have y of t, but with or without k, and so with k, the solution will just be k y of t, or not, yeah, not k y of t, y k of t. And because this is multiplied by a constant, we know that this is a constant, we can take it out of the function, so this will equal to k y of t. So this is closed under scalar multiplication, so that means that this is a subset. And that is pretty much it for this video. I did win over time, but after this is we're going to be going over linear combinations and spans, and so I'll be seeing you guys in the next lecture.